All right, so this is problem 6 on your practice test for exam 5. So we have rigid insulated container of volume, 0.02 meters cubed. So let's go ahead and kind of write what's going on here. So we've got a rigid insulated container. I'm going to draw it as a box just for, whatever. And there's reference to a paddle wheel. So there's work being done on this thing. And we've got water. So there we go. And I am going to throw on here because it says that it's a rigid tank. I'm going to say that the change in volume is equal to 0. What that would extend to is that the change in specific volume would be 0. Also, it's insulated, so my Q is 0, right? Or that's something I would assume, right? That it was a minimal volume or minimal heat transfer. And again, my volume is 0.02 meters cubed. I won't put a 1 or a 2 because it's just the same, right? If it's a rigid tank. It's fitted with a paddle wheel which contains water initially, so T1, 300 degrees Celsius, and a quality of 0.6. And then the water is stirred by a paddle wheel until we reach a temperature of 440 degrees Celsius. And we are supposed to find the amount of entropy produced during this process. Now, usually you might be given some information about the units that they're looking for. But if it's entropy, if it's entropy produced, if it's sigma that they're looking for, then it would be in kilojoules per Kelvin. And for that, you're going to need the mass. There's no way to figure out the mass. Well, is there now? There might be. Actually, there is a way to figure out the mass. Well, I tell you what. If I don't give you units, and I say the amount of entropy produced, you can give me sigma or you can give me sigma over mass. So I'll just say either one in this case because I don't specify, right, what I'm looking for. Either one would be perfectly fine. So, and I'll show you how to do both. Yeah. So, all right, give and find, assume, here's my solution. All right. So the first thing that I'm going to do is, since they're asking for the amount of entropy produced, I think I'm going to draw my, or put my entropy balance for a closed system, right? So entropy balance for a closed system, delta big S, the change in entropy contained within the system, is equal to the amount of entropy transferred by heat transfer across the system boundary plus the entropy produced. Okay, perfect. And I don't have any heat transfer, so I don't have any entropy transferred by heat transfer, so I'm going to get rid of that guy. And I'll have sigma equals delta big S or m delta little s. All right, so if I'm looking for sigma over mass, then I could divide through by mass, I guess, but it's fine. Let's go ahead and figure out how we would figure out the mass as well. All right, perfect. All right, so we should have enough information to figure out state 1, and we do because we have the temperature and we have the quality. That's two independent intensive properties with which to fix my state. So there's S1. So this, and this is all at state 1, at T1 and P1, right? So S1, and of course we have a quality here, so I know I'm going to have to use that quality in order to calculate this guy. So it's going to be S sub G S sub F, perfect. And this is all going to be at T1, 300 degrees Celsius. I assume that you can look that up in your tables. Well, you can. Let's see. So, but I end up getting for S1, I've got 4.7. Oh, how many significant figures? I'd probably, yeah. So I'd go 4.7241 kilojoules per kilogram K. But I am also going to need to get my specific volume because that's what I need fixed state 2. I know T2, but I need some other property. And the fact that they told us that it is a rigid tank indicates to me that, okay, well, I've got I've got constant specific volume. So our specific volume is going to be V sub F plus our quality, 0.6 times V sub G minus V sub F. So let's see what this ends up being. This guy is 0.01353 meters cubed per kilogram. Again, you're going to be, for this guy, you're going to be looking in table A2. All right, so now we need S2. So S2, like I said before, this is going to be evaluated at T2, 440 degrees Celsius, and then a V2, which is equal to V1, 0.013563. All right, and so I can look at my tables, might as well. Let's go ahead and pull those guys up. All right, so 440, and then we got our specific volume here. So I could see that if I look at my saturated tables, A2, I can see that my critical temperature is 374 and change. I'm above that because I'm at 440 degrees Celsius, so I need to go into my superheated tables. It's above that critical point. So here's an issue where normally, okay, so we know we're superheated, but now we have our temperature and our specific volume. And that is still enough to fix our state, even though it might not be obvious, because I don't know, it's not obvious, well, which one of those boxes corresponding to pressure am I going to go to? So what I'm doing is I'm going to say, all right, well, I know that my specific volume is this 0.135 or 0.013 and change, 0.013 and change. So let's go over here. And so what I'm going to do is I'm going to look at 440. Oop, not that. What's that? Actually, let's go that one. Okay, so I'm looking at 440 up. So if it were 440 and it was superheated, looks like, I see what I'm looking at is I'm looking at this line corresponding to 440 degrees Celsius, and I'm looking for a specific volume that's kind of close to that 0.013 number. So, okay, nope, getting closer though. 0.0, nope, I'm looking for 0.0 something. Oh, getting closer. There we go. 40. There it is. So it looks like we're going to be at a pressure between 60 and 80 bar. Why? Because my specific volume at 440 is 0.0, what was it again? 0.013563, which is between these numbers right here. So what it's going to look like, I do need to interpolate. So I'm interpolating like this. All right, so I'm going to say, all right, so at 440 degrees Celsius, I'm going to make my own little table that I'm going to interpolate with. So I have a specific volume over here, and then I've got an entropy over here because that's the property that I'm after. All right, so at 440, and my specific volume is 0.013563 meters cubed per kilogram. Well, if I were at 440 and my specific volume was at 0.05122, well, my entropy would be 6.6853. If I were at 440 and my specific volume were 0.03742, then my entropy would be 6.5190. But this is the entropy that I'm looking at for. And so I know it doesn't, it doesn't matter. Maybe I could have put this like, oh, that's, darn it. 0.0, 0.13. Stupid. Somebody was like, what? 0.013 is not between 0.05 and 0.037. My goodness. I was excited because I saw a 0.0, so I'm sorry about that. Okay, keep on going. 0.13, 0.13, 0.13. I'm getting close. Okay, getting close. Bump, dump. Oh, so close. Now I think I did it. Okay. All right, so I got a column for specific volume and entropy. Here we go. Bump, All right. So I'll actually write it in order. I'll take my time this time. 0.013563. That's my S2 value. And then the values right above and below. So 0.01222. Well, my entropy would be 5.845. And if it were this guy up here, so 0.01414, my entropy would be 5.9428. Yeah, sorry about that. Sorry for anybody that was like, what is going on? But I've got an entropy value of 5.9 and change. Yeah, so my S2 value, if I interpolate, it's going to be 5.913. There we go. Kilojoules per kilogram K. And then I'll go ahead and go over here as well. So 5.913 kilojoules per kilogram K. And it was superheated. And you got to interpolate. Okay. All right. And then, of course, my mass, well, that's related to the information that I know about volume. So I know that mass times specific volume is equal to volume. And it doesn't really matter whether I'm talking about the specific volume at 1 or 2 because it's the same at state 1 or state 2. That was one of the assumptions that I made because it's a rigid tank. And so I just calculate what mass is. So it's going to be volume 0.02 meters cubed over my specific volume, which I've got to be 0.013563 meters cubed per kilogram. Perfect. And so, yeah, what is this? 1.4746 kilograms. So should be enough to fix our, or to get our value of sigma. So I got 1.75 kilojoules per, just per Kelvin. That's it. All right. Hopefully that was helpful and not too confusing. Sorry about that. So let me know if you have any questions. Thanks.